So, very good afternoon. I welcome all the chair, the co-chair, and today's SOAP lecture presenter, Professor Gang Wang, and other participants who will be making presentations in this technical session 8, hall number D. It starts from 2 o'clock to 4 o'clock it goes. And now it's my pleasure to welcome the chair, Dr. Vineet Kumar Gahalot. He is the chief scientist at NGRI Hyderabad in the seismology division. And Dr. Vineet Kumar obtained his MTech degree in the year 1999 and a PhD in the year 1995 from University of Roorkee earlier, and now it is I.I.T. Roorkee in geophysics. And he is at CSR NGRI since 1999. Earlier, he served as faculty at I.I.T. Roorkee for the period 1996 to 1998. And then for some time in DST New Delhi from 1998 to 1999 for a very short period. And now he is the director of National Center for Seismology, Ministry of Earth Sciences, New Delhi from 2015 to 2019. And I'm happy to share with all of you that he is involved in the research related to earthquake processes, tectonic geodesy, seismology, and geodynamics. He has more than 150 research publications in peer-reviewed journals, and he is also a fellow of Indian Academy of Sciences, Bengaluru. I extend a hearty welcome to Dr. Vineet Kumar, sir. Welcome to this session. And I request you to chair this session, sir. I also have the pleasure of welcoming the co-chair, Dr. Subramaniam Ramanathan, the director, GIA Geoscience India Private Limited. And his area of expertise is in geotechnical earthquake engineering, geophysical surveys, and dynamic pile testing. And earlier he was working with Sarathi Geotech Bangalore. He was working. So, Dr. Subramaniam Ramanathan, I extend a hearty welcome to you.
Thank you, sir.
And I request you to co-chair this session.
Thank you.
I also welcome the today's SOAP lecture, Professor Gang Wang from the University of Hong Kong. Of course, formal welcome will be done by the chair. Welcome you, Professor Gang Wang. I also welcome all the presenters for this conference, Saptarshi Kundu, Hemant Srivastava, and then Arup Bhattacharya, Anushka Joshi, and Sagar Barua. Very good afternoon and a very hearty welcome to all of you. That's it from me, and now over to Dr. Vineet Kumar and the chair, and Dr. Subramaniam Ramanathan, the co-chair. Over to you, sir.
Thank you, Dr. Dinesh. So I hope that everybody is here in this hall D who are going to make presentation, and we have 2 hours time. So probably we'll have about 35 minutes for the first talk, which is kind of a plenary talk, the main invited talk here by Professor Gang Wang. Then we have 5 more presentations. So we will be left with almost like 115 minutes, 1 hour 15 minutes. So probably we'll give 15 minutes to each of the remaining speakers to make their presentation, and probably 1 or 2 questions if time permits. So I think the first talk is by Professor Gang Wang, and he's a professor at Department of Civil and Environmental Engineering at Hong Kong University of Science and Technology. It's good to see his biodata because probably we spent almost kind of overlapping time at University of Berkeley, California. I was there at McCone Hall, Professor Wang in our science department. That's where I spent some time, and he did his PhD from civil engineering from University of Berkeley, University of California, Berkeley in 2005. He's occupying lots of position. He's presently vice president of Hong Kong Society of Theoretical Applied Mechanics. He's an invited member of several committees. He's also the former president of I.I.Sc Hong Kong section. He has several publications in fact, 60 publications in reputed SCI journal. And he has also served as associate editor of soil dynamics and earthquake engineering, which is very reputed journal. I think I can, if I go on, I mean, I'll be taking too much of time. He has got several other awards. He's also he has got the Youth Award in Soil Mechanics and Geotechnical Engineering, which is considered as the highest award, highest honor for the young researcher in by Chinese institutions of soil mechanics and geotechnical engineering. I think I will not go into because most of you people must be knowing him very well. So I will not go into his entire biodata. And with this, I think I'll invite Professor Wong to deliver his lecture. Professor Wong, you have about 35 minutes, and then we can have some questions if you feel like and if time permits. Please.
Thank you, Chairman. Thank you for inviting me to deliver the lecture. It has been a long-awaiting event. I'm very excited to present some recent study on large deformation analysis of co-seismic landslide using material point method. I basically give you a background information, introducing the material point method. I give you several examples for large deformation analysis. And also I introduce a so-called multi-scale material point method coupled with other numerical method to do a large-scale simulation with a Hongxian landslide case study and some observations conclusions. We all know that the earthquake-induced landslide hazard cause many catastrophic results. For example, this is Tangjiashan landslide, 20 millions of cubic meters, a landslide, which basically blocked the river and created so-called landslide dam. So it is quite an endangered situation for the downstream. And also in the 2008 Wenchuan earthquake, about 15,000 of geohazards, including landslide, rockfall, debris flow happened, killed 20,000 people. So the Hongxian landslide, which I will give a numerical analysis, actually happened in 2014 in Yunnan, China. The landslide is 12 million cubic meters, and also it generated a debris dam blocking the New Lanjiang River and caused a kind of emergency situation for the downstream. As we are geotechnical earthquake engineering, we have many simplified methods to tackle this issue. The most famous is one-dimensional infinite slope analysis, where the earthquake loading is simplified as a static load applied in a horizontal direction. So we do the static analysis. The 2D limit equilibrium analysis can also be applied and be performed in a similar way. We have a 3D dynamic finite element analysis, which is usually focusing on a narrow, small region. Of course, recently, people try to use a material point method for large deformation analysis. It has been applied in many regions, including the soil-water interaction, underground marine landslide, etc. So why we need material point method? You can see that traditionally, the dynamic finite element analysis is mesh-based method. That means the whole domain was meshed using a Lagrangian mesh. So the mesh will deform as the body deforms. So you would have mesh distortion problem, for example, at this point. For dam analysis, you can see the mesh distortion is so severe that it cannot carry on, especially if you use highly nonlinear soil modeling. So I'll give you an example of material point method. The material method can do more than the FEM, although we can regard it as a special case of SEM. For example, particularly, it can handle the large deformation analysis, which is a very convenient tool. So talking about material point method, actually it's a combined of Lagrangian material point. So we use the material point, for example, to represent a deformable soil mass. And we have a background mesh. To conduct analysis, we have material point information, for example, velocity, stress, displacement, etc. They can be all mapped using the mapping function to the background nodes. Then we solve this so-called moment equilibrium mass conservation equation on the background nodes. Then the solution from the background node, for example, the velocity information, will be projected back to the material point. The material point will move for the next time step. So it keep on looping this way. So you can see that the material point is a Lagrangian point. It keep on deforming, but the background mesh is fixed. They're Eulerian mesh, thinking about the fluid mechanics calculation. We can implement several nonlinear soil models. For example, this one is so-called non-associated Mohr-Coulomb strain softening model. Basically, we have friction angle, dilation angle, and cohesion. This is a very classical Mohr-Coulomb model. And also these parameters can be degenerated or reduced. We call it strain softening according to the plastic strain. So here is one example here. So for example, the dilation angle is 10. Residual dilation angle can be set as 0 degree. The peak friction angle can be 40 degree. Residual friction angle can be 23 degree. Peak cohesion and residual cohesion can all reduces with equivalent plastic strain. For this example, you can see 10% or 20% of plastic strain will bring the soil strength to the residual state. It is a softening curve. So here I show you example that we have a bedrock, which is very hard and elastic, and we have strain softening materials on the surface. So with harmonic motions, we can clearly see that the top will slide it and also induce the bottom sliding case together. And sliding will keep on until the end of a stop will be deposited here. So if I look at the snapshot, you can see the top portion is sliding initiated locally here. You can see a generation of slip band. And also we can have a running down slip band deformation and running down. And here, the top soil and the bottom soil actually generate a so-called self-contact. And so it will push the bottom soils continue to slide down. So in the end, the whole deformation is 10 meter deposited at the foot of the slope. So it's very interesting to look at the interactions, so-called cascading effects, when the top portion of the slope actually moves down, exerted about 50 kilopascal of the shear pressure on the bottom. So actually the bottom layer would not be able to slide if without the top layer. So these two events actually show you a cascading failure from the top to the bottom sequentially. And we can handle the material point, soil water coupling the material point. It's a common strategy is to use 2 layers of material point. We have represent a water points and a solid point. So we have to obey the Darcy's law, balance momentum, pore pressures, degree of saturation change, soil water characteristic curves, and nonlinear soil behaviors, etc. So here I show you a kind of rainfall-induced slope failure case. When there's a rainfall, you can see the top of the soil will quickly be saturated. We have accumulated water on the surface. So the surface begins to generate shallow sliding. When the water actually migrated down to the deeper, so it generates a deep sliding all the way to the here. So this soil water coupling can deal with unsaturated case, for example, you can see the pore water pressure is negative. That means the metric suction. With infiltration in the rainfall, the water pressure actually reduces to 0. If you continue to infiltrate the rain, you can get a positive water pressure as well. So we have a very famous San Fernando earthquake dam failure in 1971, which is kind of a classical example for studying the liquefaction-induced dam failure. So at that event, the PGA of 0.5 G was recorded on the site. So this is a best case history of liquefaction effects on the dam studies. So Professor Seed and his co-workers actually studied this behavior and found that there's a liquefiable zone on the front surface, on the upper surface of the dam, which is liquefied and cause a large deformation sliding into the dam reservoir. So on the downstream, because of a building of a reinforcement burns, so this downstream is relatively stable. So we utilize a so-called bounding surface plasticity model and try to capture the liquefaction effects. You can see the model can actually capture the progressive build up the pore pressure and the reduction of the effective stress and the generation of nonlinear stress strain loop. So here is our model using the NPM. As I said, we have 2-point material model. We have explicit points for the water. So we meshed a little bit about the water reservoir. Later on, I'll show you that actually the water, when the sliding into water, actually there might be some interactions here. And also the dam, we use a solid material point to model it. So we have a roller fill zone. We have the clay core zone and also 2 hydraulic fill zones. We noticed that this part was liquefied during the previous study. As a bounding surface model, we have quite a lot of parameters, which was taken from previous studies, especially the hydraulic fill is liquefiable. Others are not liquefiable, specified by a parameter here. So here I try to give you a video to see how the dam slided. You can see the earthquake start shaking right now is almost by 10 seconds. So the dam actually generated a liquefaction upon here. So this is now 20 seconds. The earthquake actually was stopped. Earthquake stopped, but the liquefaction will continue. It's a little it's broken. Okay. Share screen again. You can see after 20 seconds, so liquefaction will continue. And keep on moving until it reaches the final deposition point. Notice that the shaking is only about 20 seconds, but the deformation actually lasted for more than 60 seconds. This is a comparison of final configurations. You can clearly see that the sliding actually is about 50 to 60 meters after the liquefaction, which is well captured by the material point method here, compared with the profile by Professor Seed. Previously, you can see the final element analysis was also conducted. They have quite a lot of problems to handling the mesh distortion problem at the front. So relatively speaking, previously the FEM cannot get that large deformation up to 50 meters. So now, at last, we come up with a so-called multi-scale SEM MPM framework. We know that NPM is quite a time computational cost. So, but it can calculate, it can compute the progressive failure, runoff, and deposition process. Can we combine the large-scale regional ground motion simulation, for example, by the spectral element method? We can actually model the whole process of wave from fault rupture to the wave propagation until to the site. So SEM give you a brief introduction that it's high order finite element method. So we can use, for example, fourth order or fifth orders for one element. So we'll be able to capture a large scale wave propagation. So for example, this is what we did for a very large scale of wave propagation in Hong Kong. The dimension is almost like more than 20 by 20 kilometers across. So we have to couple the material point method with the spectral element method. Spectral element method uses coarse mesh, elastic material property. So material point method use fine mesh, but nonlinear soil. So this is how we constructed the coupling using the so-called domain reduction method. The domain reduction method was first proposed by Professor Biliak for the finite element analysis. Here we just modified the method, actually try to couple SEM and NPM to different computational domains. So we set up a mesh, SEM mesh, which is big and coarse, but within it, it has a boundary. We have a material point mesh actually inside. So here we have so-called the force transmitting layer. So in this layer, we use interpolation of coarse mesh from SEM until to the fine mesh to the material point. So there's a couple of theoretical considerations. The basic idea is SEM, they have a fault source, but they can also compute the so-called equivalent force acting on the boundary. So in the NPM analysis, we need to apply this equivalent force acting on this boundary to the NPM domain, and then we can conduct the fine scale analysis. Notice that the SEM is elastic, coarse mesh. The NPM is nonlinear and finer mesh. Of course, we have to use something like absorbing boundary conditions applied to absorb the waves to make it very good. So as I mentioned, the Ludian earthquake in China, 2014, actually induces more than 10 million cubic square of sliding mass. So here is the New Lanjiang River. So here is the landslide area. So in order to model this event, we actually created a large-scale SEM, which had modeled the fault rupture. And the Hongshiyan landslide is here. And luckily, we have a monitoring point called LLT. It records the real earthquake motion. So we can use this record to verify whether our SEM is good enough to capture the wave propagation. Based on the fault inversion analysis, we can construct the slip distribution along the rupture plane. So you can basically say that the seismic moment, the so-called energy, actually was released within the first 10 seconds. The rupture of the fault is mainly shallow. It's shallower than 5 kilometers. Therefore, although the earthquake is not very huge, but it generates a lot of damage. So globally, the shear wave velocity profiles can be actually generated like this. So we set up so-called SEM model to model the rupture process. I play the video here. You can see this is a strike slip fault, and wave actually is generated from here. Here, the Hongshiyan landslide area. So the shaking actually can be simulated from the rupture to the fault. So here is some snapshot to give you a better analysis. In the 6 seconds, you can see the wave, this is wave velocity propagated all the way towards the site. The site is this area. So you can look at the site, the Hongshiyan site. So the wave actually will arrive at the site location around 7.5 seconds and passed around after 1 or 1.5 seconds. So we can compute the equivalent nodal forces on this, we call the gamma layer, fictitious boundary. And we use this equivalent force, try to do the fine scale analysis. As I said, the LLT is recorded. We can see the simulated motion and recorded motions are quite close to each other. This is acceleration comparison. The acceleration is close to 0.8 g by recorded. So here actually is much larger because of the topography effects. So we can also compare the velocities at the recorded station. Here is the site location. We can clearly see that the PGA is 1.7 g, it's very huge. And peak ground velocity is around 150 centimeters per second. So here we try to combine these two analyses to conduct the multi-scale analysis. Here we constructed a material point method, which is 3.5 times 3 kilometers in dimension. And you can see the fictitious boundaries apply here. We apply the equivalent forces. We have several monitoring points, P1, P2, P3, etc., around here. So you can clearly see the mesh is 20 by 20 by 20 meters with 8 material points in each cell. We can make it smaller for better results, but this is our computational capacity right now. So we have a string softening Moore-Coulomb model for this part. Outside, as I mentioned, is the elastic material. So I try to manipulate this one and to make this start together. You can see that when it starts, when the two things are started together, so the wave began to propagate it all the way to the Hongshan landslide site. So you can see here, the landslide started when the strong wave arrived. So when the wave actually dissipated away, the sliding continues all the way down to the river. So this is a river deposit. So in the end, you can see the Hongshan landslide actually reached the river and blocked the river channel as indicated by real case history. So you can clearly see the area, we didn't pick it on purposely, but the area actually almost coincide with a real landslide event. So this is a kind of very encouraging situation. And we can compare, for example, the ground velocity distributed. So before 6 seconds, there's ground velocity is less than 1 meter per second, which is due to the wave propagation. So at 7.5 seconds, 8 seconds, so the wave actually is passed away, but the mass began to sliding down and accumulate quite high velocity, like 20 meters per second during the downslide sliding until they deposited here. So you can see the progressive landslide process. The vertical sliding distance is more than 500 meters. Our maximum velocity is greater than 20 meters per second during the sliding. So we can compare, we can have a progressive snapshot. You can see the generation of shear band. So the shear band actually is progressively go down, and erosion happened when it's sliding down. You can see the profile up to here. So there's a deeper entrenchment going to the sliding area. So the sliding mass erodes the underlying material into a landslide. The PGA is this location is 1.3 g. And we can compare the MPM acceleration and SEM acceleration at the same point. So we position here without here because a landslide would affect the acceleration. We don't want a significant effect. So we select the point A. You can see they're roughly reproducing each other. That means the domain reduction method can reproduce the larger domain analysis. So we can look at the deposition profile. So the red line is a field observation. The dashed line is our simulation. So this is cross sections along the river channel. You can see the deposition profile roughly coincide with the case history. So the total sliding volume based on our numerical simulation is 15 million cubic squared, which is close to the observed data, 12 million cubic squared. So we're quite satisfied with this trial. So there's several thoughts. First of all, we need to improve the computational efficiency. You can see we can use probably unstructured mesh, adaptive meshing technique to capture the sharper shear band, because not everywhere you need very, very fine mesh, especially this sliding area, you need finite mesh. We need to take care of a local near surface hydrogeological condition. Right now we use average soil property, probably the soil water interactions and maybe combined water effects, etc., can actually cause the different sliding scenario. The cascading hazard evaluation, you can clearly see when the loose material was deposited on the river channel, it created a different hazard. So the landslide dam actually need stability analysis and evaluation post the earthquake landslide. So I report you a news that in 2020, the Hongshan landslide actually deposit, because it's so much, we cannot move it, has been converted to a returning dam and used to build a new power station, as shown here. So quickly I concluded that we can advance the numerical method like MPM method and to study the large deformation analysis and go beyond the finite element analysis. Further, we can develop multi-scale material point method and SEM framework. We can take account of the bigger geology and earthquake ruptures scenarios, the coupling regional scale analysis with local scale deformation, bridging the gap between engineers and the earth scientists, seismologists. So my study was supported by many students like Dr. Feng and Dr. Chang and my students and collaborators in Tsinghua University and grants from Hong Kong and China. Thank you very much.
Thanks a lot, Professor Wong, in finishing in much ahead the time given to you. So can we have one or two questions if you like, Professor Wong?
Yes, please.
Is there anybody, either you can post them here in the chat box or you can ask directly because we have some time.
Okay, I get one. Chairman, maybe you want to read?
Professor Wang, Dr. Subramanian here.
Hello.
So, yeah. So I would just like to understand like how it could be computationally efficient when compared with finite element methods.
The computational cost compared with the finite element method may not be that much depending on, for example, your complexity. For the dam, that dam I remember is like in my server is around like less than 2 days, 1 day or something, which I consider to be reasonable still. Because in FEM you still need to handle the pore pressure generation and UP formulation, etc. But for MPM, you need to handle 2 layers of material points. So you need one more operation is to map your information to the background and do the equilibrium analysis as solve the momentum equation. You need two more additional operation, but that operation I think is not that costly compared with the FEM. I would say maybe 50% more effort you need to spend.
Okay. And in fact, when we are showing about the material properties, you had shown one parameter named as shape factor. So how it actually signifies?
sorry, you said the material point method use a shape
Yeah,
factor?
shape factor. So that is based on the grain sizes of the soil, or like how you are arriving at the parameter.
Oh, you mean the softening shape factor, right?
Yeah, strain
Okay.
softening parameter. Yeah.
Yeah. I think based on the soil mechanics experiment, I would say roughly 10% or 20%. You need to reduce down a lot already to reach almost a residual state. Yeah, based on my review of the experimental data, like 10% of strain or 20% strain is already reached the residual value. The reason is why, because for many soils, they have a C and a phi. The cohesion would reduce a lot in the residual state, but friction angle may not be. You can have a slight reduction or no reduction in friction angle, but cohesion under the large deformation may be already diminished, especially if I model the landslide, which is fractured rock. In the fractured rock, in my example, it has 1 megapascal of cohesion. When the sliding down, it's already moved, so and shear through, so there are virtually no cohesion, but still maintain a friction. So the friction virtually cannot reduce much. So it's all depend on the soil parameters and your simplification. I realize it's also too very simplified way, but people realize that residual state actually is important for the modeling the deposition. If you don't introduce the residual, it might be too strong to slide. It cannot slide down.
Thank you.
So
yeah, I mean, this is quite an interesting topic, and I mean, co-seismic landslide is we have seen. I'm basically from seismology background, so I have nothing to comment. But yes, this is a topic which is very much of great interest, especially after Kashmir earthquake, where lots of landslides occurred, and of course some of them dammed some of the rivers. So there was how they're going to perform later on, right? And then of course the other big issue what we have is the example from 1950. You call it Chayu earthquake, or we call it Assam earthquake, which occurred somewhere in northeast India and southeast China. So it caused lots of landslides, and the Brahmaputra River, what we call, which is Tsangpo River in China, that was influenced quite a lot because of landslides triggered by these by this earthquake. So that's a big concern for all of us. Thanks a lot. Thanks a lot for your
Professor Vineet. So there are two questions in the chat box. Can we attempt it now?
Yeah, sure. I mean, we
okay.
Yeah,
I can answer very quickly. The first question is, what model is used to depict the flow or rainfall-induced landslide, and will it behave as a non-Newtonian flow after scattering saturation? Yeah, I think this is a good question, because right now in our simulation, the situation is mainly dry landslide. So if you want to model the transition from for example, the solid to the fluid, I think you can refer to Professor Soga. He proposed some kind of a viscous model. Basically, the material will behave like a solid, and when they go, the viscosity can actually kick into it, become a non-Newtonian fluid. But in my simulation, it's mainly a rock slide, solid slide. So the second question is how the contact model between FPM and MPM domain are the quadratic elements not capable of capturing liquefaction. The MPM and the SEM and MPM domain coupling is done not by contact. The contact is a handshaking method, which is we use overlapped mesh. but we call it equivalent mesh and apply to the small domain, which is called the domain reduction method, proposed by Dr. Bilek. Therefore, it is not a directly handshaking coupling. There are many other coupling methods, I will see. So I think it could be a game changer if we combine the method together by combining the seismology study with a geotechnical study together. I think this is the part we need both expertise. SEM, we need a seismology study, and NPM, we need geotechnical geomechanics. Thank you very much.
Thank you, Professor Wong again. Thanks a lot. So,
Professor Wang, are you there?
Yeah, I'm here.
Just I have one question. So whether this MPM method can be used for this pile driving studies, soil structure and traction problems?
Yes, actually, because contact can be established between the soil and solid. Actually, we also model something like backfill and the returning wall. It looks like similar to the finite element. So the problem is if you don't have a large deformation, so the benefit is not that great compared with the FEM because both are small deformation. So you don't get more compared with FEM.
Yeah, but in case of pile drivability studies, I believe that large
you're right. You are right. The pile driving is an outstanding example because FEM, you handle the pile driving, you have to slip the nodes, you have to penetrate, and maybe you do the Lagrangian or Larian remeshing.
Adaptive meshing.
Yeah, adaptive remeshing. But this, you don't need to. I think it's naturally can calculate the pile driving. Yeah, it is one example. I agree.
Thank you.
Thank you.
If there are no more questions, so I will hand over to Chair Mr. Vinit Kumar. Yeah, please go ahead, sir. In concluding this session.
Thanks a lot. Thanks a lot, Professor Wang. Thanks a lot, Ms. Mehbooba and Saptarshi Kundu. Then I think the other person who was Bhattacharya, I think he has left the session.